Now, I believe somebody asked for some explanation of the dot product and maybe how it applies. So I'm going to give you a little synopsis here, and I'm going to use that to also motivate a definition of work and energy. And we'll build more on that definition, but let's consider this. Let's say a car is moving in this direction, okay, to over in that way. Now, if I get behind the car and push it, and if I push it for a while and push it pretty hard, and if it's moving reasonably fast, I'm going to get out of breath pretty quickly from the effort of pushing it. I'll be sucking wind before long. If, on the other hand, the car is moving in this direction, and I push from this way, I push perpendicular to its direction of motion, I don't contribute anything to that car's motion. Unless I happen to be strong enough to slide the car across the road, to slide the tires across the surface of the road in a direction that the car doesn't want to go. And I guarantee you I never was strong enough to do that, and I'm certainly not strong enough now. Okay, so in this case, I might exert a little effort, and of course I've got to keep up with the car, so I've got to keep moving this way. So I might do a little bit of work, I might get a little bit out of breath, and just from the contraction of the muscles and the effort of pushing in this direction, I might get a little bit out of breath, but I won't get to the point where I'm sucking wind. Okay, the effort is much less. The reason for that is that in this case I'm doing work. That work is contributing to the kinetic energy of the car. In this case, I'm not doing work, and the effort I exert contributes nothing to the kinetic energy of the car. Now we'll build on that idea, but let me use that to motivate the idea of a dot product. So let's say that delta x is the vector that represents the displacement of the car. Okay, the car starts here, it ends up somewhere down there, so delta x is a vector from here to wherever the car ends up. And F is a vector that represents the force that I'm exerting on the car. Now, if I'm exerting the force in the direction of motion, then all the force I exert, turns out, goes into doing work on the car. Now, that work could speed up the car. It could just help the car overcome frictional resistance. The car could be on an incline. It could help the car climb the incline. In general, the force I exert might be in a different direction. There might be a bunch of us on the back of the car, and the force I'm exerting is over in that direction where the car is moving in this direction. I might be kind of on the bumper someplace. To get a handle on the effect of that force in helping the car move, speed up, climb an incline, overcome friction, whatever it happens to do, I can break the frictional force into a component parallel to the motion, and I might as well draw a component perpendicular to the motion. The parallel component contributes to the work. So I'm going to say the work done, and I'm going to call that delta W, the work done, delta W done as the car displaces a distance, or through displacement delta x, is going to be F parallel times delta x. So again, just making, I'm not sure what my sentence is going to be, but the F parallel delta x is going to represent the work that's actually done on the car. The F perpendicular represents the part of the force that I'm exerting that doesn't do any work. So the only caveat here is that F parallel delta x is going to be positive if F parallel is in the direction of delta x, and negative or zero otherwise. If I'm pushing in this direction, I'm going to have an opposite effect on the motion of the car or whatever the car's accomplishing energy-wise. So I'm going to tend to dissipate energy. I'm going to tend to reduce the energy the car gains or reduce the change in the energy state of the car. And none of that's going to make a lot of sense right now, but the fact that if I exert a force this way, I have an opposite effect of the one I would exert if I exert the force in this direction. So there's a definition of work, and we're going to use the definition of work to motivate the dot product. The definition of the dot product is that, and I'm going to use F and delta X for my two vectors. We could use A and B, but I'm going to keep the meaning, retain the meaning of the example that I used to motivate. So F dot delta X is the dot product of F and delta X, and it's simply equal to the magnitude of F times the magnitude of delta X times the cosine of theta, where theta is the angle between F and delta X. So I've drawn that down here, I've drawn F here, I've drawn delta X here, and I've labeled the angle theta. It should be very obvious that this F parallel vector, the one that we're really interested in here, has a magnitude that's equal to the magnitude of F times the cosine of theta. Okay, by this right triangle. The F parallel runs along this adjacent side of this right triangle, and F is the hypotenuse. It follows immediately that this vector has a magnitude equal to the magnitude of F times cosine theta. There's another advantage to the cosine of theta, and I just realized I should also have the magnitude of cosine theta here. There's another advantage to cosine theta in that if theta is over here in the second quadrant, so that, or the third quadrant even, so that F is acting in a direction opposite delta X, the cosine of theta is going to go negative and give us a negative result here. I've got the magnitude of F parallel here, and I've had to put magnitudes here and an absolute value here, but when you do the dot product, the cosine of theta does not have absolute value signs around it. So that if F and delta X are in the same direction, cosine of theta, well, theta will either be in the first or third quadrant, giving you a positive F parallel. And if F is acting contrary to the delta X, the cosine theta will be in this, well, theta is going to be a second or third quadrant angle, and the cosine is going to be negative. So this formula takes care of the caveat I had here. When I made this definition, I had to say that this thing's positive, F parallels in the direction of delta X negative. Otherwise, this definition, this dot product, is going to take care of that completely. The nice thing about a dot product is it's really easy to calculate it. Let's say that F is equal to Fxi plus Fyj, and delta X is a delta Sxi plus delta Syj. Then F dot delta X is going to be calculated by just a very simple calculation. We simply multiply the I components here, the Fx and the delta Sx, and the J components, Fy and delta Sy. So that's it. That's how we calculate the dot product. If we know the components of the two vectors, we very easily calculate the dot product of those two vectors, and that calculation, what we get from that calculation, is going to be equal to the magnitude of the x vector multiplied by the magnitude of the f vector multiplied by the magnitude of the x vector times the cosine of the angle in between them. And again, if these vectors are such that the f reinforces the delta x, you're going to get a positive result here. If f is moving against delta x, it's going to come out negative, and it's all going to be automatic in the calculation. Now I could easily go into the reasons for this equality, but yeah, that gets into the mathematics of it, and we're just going to use this. But I do recommend in your mathematics course, for example, if you're taking vector calculus now, You really want to understand why this is so. You don't want to just use this as a formula. You want to have deeper understanding. Even though if you don't have time to develop that understanding or aren't in the course, it's probably not worth your time right now. And you can get along just fine just knowing the properties of the dot product.